When working mod n, we found that we could add two numbers by adding any number they were equivalent to. This means we could reduce our terms mod n and work with smaller numbers. Can we do this for multiplication as well? Let's find out. Let's find a product, mod 15, and we'll do it in two ways. First, we'll find the product and then reduce. Then we'll reduce the factors first and then multiply. So we multiply, divide, we have a remainder, and so the product is congruent to 8 mod 15. On the other hand, if we reduce first, we find that 29 is congruent to 14, and 22 to 7. The product is, and then dividing we find, and so the product is also congruent to 8 mod 15. Now, we could find other products this way, comparing what would happen if we multiplied first and then reduced, but since we already suspect we can work with reduced values, let's try to prove that instead. So, a useful idea, rewrite theorems as conditionals. So, let's rewrite this as if A is congruent to R1 mod n and B is congruent to R2 mod n, then their product is congruent to R1, R2. So the reason that this is useful is that you can always assume the antecedent, the if portion of the conditional. So suppose A is congruent to R1 mod n and B is congruent to R2 mod n. Remember, definitions are the whole of mathematics, all else is commentary. Since these are congruent, we know their difference is something times n. Now, we want to end by saying that their product is congruent to the product of the moduli. And again, the reason that definitions are so useful is that in order to get here, we must have the difference being something times n. And now we need to form a bridge from our start to our end. And we do need this product A, B, so let's go ahead and solve these two equations for A and B. And then we could find their product. And we want to find the difference, so let's rearrange that. And we see that this difference can be expressed as something times n. And so we get our proof. And so this means we can take an expression like this product, mod 7, and work with the reduced values. So we can reduce mod 7 to get, and so the product will be, which we can reduce. And this is the basis for something known as the fast powering algorithm. In certain applications, we'll want to find a power of a number where the exponent is a very large number. We can do this efficiently using the fast powering algorithm. We'll find our number, square it, square the result again, and importantly, we'll be reducing these mod p, and then we'll select the powers that multiply to our exponent. So, for example, say we want to find 7 to the power 560 mod 13. Well, 7 is congruent to 7. 7 squared, well, that's 49, which we can reduce to 10 mod 13. We'll find 7 to the 4th by squaring 7 squared. But 7 squared is 10. 10 squared is 100, which we can reduce. 7 to the 8th is the square of 7 to the 4th. We know that 7 to the 4th is 9, so this will be 7 to the 16th is 7 to the 8th squared, which will be 7 to the 32nd, 7 to the 64th, 128th, 256, and 5/12. Now we'll select the powers that give us 7 to the power 560, and those will be, and we know that these are 3, 3, and 9, and so we multiply and reduce.